Hello, everyone. My name is Praveen Kundurthi, and I'm one of the developer evangelists at Intel. And along with me is Bob Cheeseborough. And as Ray mentioned, Bob will be monitoring the chat window and answering any questions you got. And even I will be monitoring periodically in the chat window. And with that, let me get started. So this is going to be the second part of the series for data parallel essentials for Python. And we'll be covering some of the use cases to the last talk that, we covered the basics of the data parallel essentials for Python and the data parallel control. With that, let's go into the agenda. And we already covered the overview of oneAPI and AI Analytics Toolkit. But I'll just brush it very briefly. And the main topics today will be, we'll be going a little bit into details of the basics of machine learning. We'll start with the basics of machine learning, and we'll talk about pairwise distance and what type of algorithms this pairwise distance can be implemented in. And we'll see multiple ways of implementing the pairwise distance using ngit decorators, kernel decorators. We'll also introduce you to Intel extension for scikit-learn, where this particular helps in the for a different calculation of pairwise using the scikit-learn. And we'll also look at some of the compute follows data approach, and and we'll also do the similar things on Black-Scholes. And finally, what we'll do is, we use tools like Intel vTune or and Intel Advisor, and generate some GPU offload reports or GPU hotspot reports, and use the Intel Advisor to generate a roofline report, analysis report. And we'll just try to see what are the commands that used to generate those, and try to briefly look at the reports and analyze those. And we'll do some hands-on exercises on the Intel Dev Cloud. So with that, just let me cover this again. We talked about this in the first series, but we already know that the current programming challenges in the current data-centric world is, there are different types of hardware. They got different languages and libraries, and they're all unique, and it requires, maintaining a whole different set of code bases, right? And with this inconsistent tool support, there is little ability to reuse, and this is a challenge, right? And the solution we already talked about is oneAPI, and the goal of oneAPI is to deliver a unified software development environment across CPUs and other type of accelerator architectures, right? And the goal is to deliver a unified language that provides full native code performance across CPUs, GPUs, and FPGAs, right? And we already talked about the basics of Intel AI Analytics Toolkit, right? So just to give an overview again, with the growth of AI, machine learning, and data-centric applications, the industry needs a programming model that allows developers to take advantage of taking the advantage of these processor architectures. So if you see TensorFlow, PyTorch, the deep learning side, they support the oneAPI industry initiative, and currently it supports Xeon process, and we look forward to using oneAPI in the future architectures. Similarly, if you come to the machine learning side, right, we got the Intel extension for scikit-learn, and we got optimized versions of the scikit-learn compared to the stock version, with a wide variety of machine learning algorithms like dbscan, k-means, k-nearest neighbors. We'll introduce you to scikit-learn in this class, and we'll also run a simple pairwise example using scikit-learn, right? And if you come to the bottom part, we got the Intel optimized Python. We're covering the Numba part in this session, which is DPEX, we call data parallelations for Python. Along with that, we got the NumPys that are based on oneMKL under the hood, which does mathematical computations like SYPy and stuff. With that, let's actually talk, because I talked about in my agenda slide that we'll be generating some vTune GPU offload reports and GPU hotspot reports, right? So let's see what this vTune actually gives, right? So vTune actually comes as part of the oneAPI based toolkit installation, and it's actually a very popular tool that multiple people use for profiling their applications, especially this actually profiles very popular languages like C, C++, Fortran, Python, Java, etc. It's actually helps to analyze and find and optimize the performance bottlenecks across CPUs, GPUs, and FPGAs. Bob, can you just heard a sound, a beep sound? I just want to make sure I'm online. Can you hear me, Bob?
I can hear you fine, Praveen.
All right, thanks. Yeah, sorry. I had a beep that I thought I got disconnected. So we talked about a little bit on vTune. I'll also cover what advisor, about Intel Advisor. Intel Advisor, a tool that gives you the right information for developers. It actually, it gives the recommendations to make the best design and optimization decisions. It helps determine if your code will benefit from offloading to an accelerator even before you have the hardware. In this session, we'll be covering the roofline analysis. The offload advisor mostly comes for the C++ code and standpoint, but I can give you an overview of what offload advisor does. It determines which parts of code will benefit from offloading to the accelerator. And it actually, it gives you what are the best parts of the code, the loops that you can offload to, and what are the poor performing, what are the loops that you don't need to worry about to offload to. So it gives you, the most profitable loops and non-profitable loops, to make your design decisions before you start offloading your code. And the second thing is we'll talk about the roofline analysis. It actually helps you optimize your, identify if your code is CPU or GPU compute, like if it's a compute bound or memory bound, and it gives a lot more analysis of memory, where it shows you the roof lines and the maximum you can attain in that. So there's a lot more information you get from the roofline analysis chart, and we'll be talking that when we actually do the live session on the roofline analysis. Vectorization optimization is, it enables vector parallelism to improve efficiency, and threading advisor helps you testing multiple threading designs, and flow graph analyzer, if you got multiple kernels which are chained or dependent on each other, this flow graph analyzer will help you identify the dependencies between the different kernels, and so that the data race conditions can be avoided. So this is a whole set of tool that comes with as part of the oneAPI based toolkit, and it can help you during the design phase, and also to profile your applications using different tools. So this is the actual roofline chart that I'm talking about, and so it's going to be roofline analysis is going to offer a very, very efficient way to characterize your kernels. It visualizes how far you are from your ideal performance on your current hardware, right? And so in order to generate a roofline analysis report, your application must be at least partially running on a on a Gen 9 or DG1 graphics GPU, and also the offload must be implemented either with OpenMP or SYCL or OpenCL, and use any version of the Intel Advisor. So the DPX is wrapping top of the SYCL. So Intel Advisor or roofline also can be generated for the Python applications that we'll be showing you today, right? And generating a roofline model on GPU generates a multi-level roofline where a single loop generates several dots, and each dot, if you see in this, each dot can be compared to its own memory. If you see GTI, and you can compare it with its own memory, how much peak it can be attained, right? So the chart can be used to identify not only where bottlenecks exist, but what's likely causing them and which ones will provide more speed up if you optimize the GPU, optimize your memory and compute. So as we talked about the tools, and let's also talk about the development sandbox, which is Intel DevCloud. And so if you see talked about Intel AI Analytics Toolkit, a base toolkit, and it comes with a lot of tools, right? So it's a lot of software to install, and the easier way for you to get started is create an account in DevCloud. It just takes a couple of minutes. Just create an account in the DevCloud and get started. Launch the either you can connect using the SSH or you can connect using Jupyter. But as we are doing all the live sessions on the Jupyter notebook, you can just start with the Jupyter environment and directly get started. So I can provide you the link in the chat window. Let me paste the link so that I can give you a couple of minutes for you. So once, so you click the link, and if you don't have an account already, please create the account. If you already have an account, you can go to devcloud.intel.com, get started. Let me actually share my screen and show you how to get started with the DevCloud, and so that let me share my browser. All right, hope you're able to see my browser. So I already got an account, and once you create the account, you should land somewhere in this page. So go to devcloud.intel.com, oneAPI, get started, right? Click on get started here, and you go here, scroll down, and you see a button called Launch Jupyter Lab, right? So you click on Launch Jupyter Lab. And you should see the Jupyter environment for you loaded up, right? For this demo, we to clone the GitHub repository, right? Let me provide you the link to the GitHub repository, and go to my chat window again, and I'm going to paste the command to git clone the command, right? So once you are in DevCloud, right? So click on the plus icon on the top. So it launches a new window, right? Scroll down, click on terminal, right? So this is your Linux terminal on your DevCloud, so you can directly interact as a regular Linux user, right? So let me create and make directory temp, okay, make directory cd demo, right? And what I do is I paste my command git clone. I can clone all the notebooks, whatever the required material that's required for this class. So let me know if you're able, if you've got any difficulties in connecting to DevCloud or creating an account. So, Bob is there and I can help you, but, please make sure you create an account and you be in a position where, you will be able to, you are able to download the course material into the cloud account so that you can run the samples directly, right? And once I'm here, right, I can actually go to the new demo that I just downloaded and go here, and I got my all the Jupyter notebooks available here, right? So click on welcome.ipynb, and you'll have a sort of a README, and you can go through all that. So whatever I'm teaching in the 3 series, these are all clearly, all these notebooks are clearly detailed, and these are self-learning, right? So the modules we'll be going through today are 3 and 4 and parts of 2, just to get introduced again. We already did 1 before, right? So you can click on that and click on the notebook and, to get started, right? So this is just a starting point. So you create an account to DevCloud. Please make sure you download git clone from the GitHub repository and get ready so that once we come to the hands-on session, we can run the samples, right? So if you see, this is all the software is installed, oneAPI required software is installed here, and this is on the login node, and you need to use a qsub command to a compute node where all the GPU got the GPUs. So you submit a job to a GPU node, and you get the results back after computing on the GPU. So that's how the DevCloud works, but we can come back later once we start talking on the slides. So let me switch back to my slides. And as I mentioned, if you got any questions on creating the DevCloud account, please post in the chat window so that either me or Bob can help you out. So we talked about DevCloud. We saw how to create and how to access the DevCloud, how to launch the Jupyter notebooks, and how we downloaded the material, right? And so we already talked about the basics of this, but just to recap. So data parallel essentials for Python, which used to call as DPCPP before. It is a suite of packages implementing a common programming model for XPU offloading from Python, right? And if you see in this, the packages in data parallel essentials for Python, it provides, the building blocks for developing Python packages that use the SYCL. ChronoSYCL is nothing but, it got the heterogeneous and the parallel program computing capability. And what this offers is a wrapper around SYCL. So, Python programmers can leverage developing parallel applications using data parallel essentials of Python, right? So, and essentially it brings SYCL classes and USM allocators. There is a DPCTL DP control layer, which actually, interacts with the actual devices using Python, and it's called. Then there is a tensor API, which is Dpctl tensor, which is a standard, Python array API based tensor, which will use specifically in the compute follows data approach, where we manually, or we actually copy the data from host to device using the compute follows data approach. And finally, the Numba-dppy extension, right, which is which is used to offload to SYCL devices. It's a standalone extension to Numba.jit compiler, as mentioned, right? It adds SYCL programming capabilities, and It's packaged as part of the Intel distribution of Python that comes with AI Analytics Toolkit, right? And that's what is the basics of the data palaces for Python, and also data parallel control, right? We already talked about this, but as just a nutshell, it provides a lightweight Python wrapper over a subset of Chronos SYCL APIs. So, you can access the devices, you can connect to the, you can actually get the device information, you can connect to a device, you can create a queue and submit a job using the DPCTL layer. So there are 4 modules in DPCTL, right? The first is DPCTL dot, tensor, as I mentioned. This is a array specific, Python specific array API, and we use this DPCTL tensor to actually manually copy your code to the device and stuff, right? We got the DPCTL memory, which wraps the USM allocators, where USM is unified shared memory, which we already covered in the last session. And the DPCTL main layer, as mentioned, talk to the device and stuff, right? So this is the data parallel control we talked about, and compute follows data approach, which we covered in the last session. It's based on the Python array specific APIs, right? So the main thing is the computation happens where we copy the data from, right? So the programming model is based on the notion of exactly the computation taking place on the device where the memory was allocated. We already talked about different types of, if you see in this, right? The first we are calling a DP array, creating a DP array, and which is actually an executing the default device. And in the second box, we are creating a DPNP array or a NumPy array, right? And we are actually creating the device here and specifying the GPU. So, this is the second way, and we are calculating. So the computation is happening where the device is. And the third one is not allowed, where you got 2 different data on 2 different devices and you're trying to calculate this, where this is not allowed, right? So the main thing to take it from this slide is compute data means computation on the device where data is placed, right? And we already talked about this programming model. So, in the previous slide, so we can skip that. So the main thing we can take away from the slide is what does numba.dppy offer? Just to cover briefly again, right? The first is numba.jit, which is array style programming, where, this is called automatic offload approach, where you're using numpys and, so once you use the numpys, this will automatically directly detect the data parallel kernels using these numpy expressions, and it automatically offloads to the GPU, to the offloaded device. The second is explicit p-range loops, where we use numba.prange specifically, and we call an explicit for loop. So this will be sent for parallel execution and is triggered whenever a numba.jit function is called. And the third approach is GPU programming style, which is called kernel decorator. And this is very similar to the Numba's GPU backends, where you use the kernel decorator. And this is very similar to SYCL programming in C++, where you use a relatively low SYCL kernel, which is directly written in Python, and you offload to your device. So if you see, I'm getting the global IDs, which is a SYCL OpenCL programming style. Global ID is nothing but the complete single item in the complete global iteration space, right? You get the global IDs of those elements, and using a program. This is very common in the GPU programming. Programmers who already have SYCL and GPU programming experience. And there are several advantages features that you can take, such as synchronization, fencing, like using atomic fences, using the local memory, shared local memory and stuff. So this is open style kernel programming, which is the third programming style. And we covered this, but I want to cover this fast. And so I'm using the NumPy here, using the ngit decorator. I'm using a NumPy, and this will be automatically offloaded, right? This is automatic offload approach. And the second is explicit p range, and we are calling the p range explicitly creating a for loop and then offloading to the device, right? And the third is the kernel decorator, and we got a driver function, and we're getting the global ID, and we're doing a simple vector addition using the OpenCL style programming in Python world, right? So now let's come to the basics of machine learning, and we'll talk about what are we going to cover in the pairwise distance, and so I'll cover very basics of machine learning slowly, first 4 slides, and then slowly come into the pairwise distance. So we'll have a clear picture of how the direction where we are going, right? So we already know there are 2 types of machine learning. The first is supervised learning, where we'll know it involves situations where there is a known outcome. We got lots of previous data or historical data, right? And the goal here is we'll take this first. We'll take this small subset of data, and we'll train it, and then we'll use some training data and we'll predict these outcomes. So this is the supervised learning, right? For supervised learning, you need the X values as the feature data, and the Y values as the target variables or labels that we talked about, right? And second is unsupervised learning, where the data points we don't have an unknown outcome, and we'll also cover this, right? So supervised learning, we know, and this is split in, again divided into 2 types depending on the type of data that we got, right? So the first is a regression, and the problem. So in this, the outcome is a numerical number, like a continuous number. For example, if you want to predict some box office revenues or housing prices, etc., right? So the regression is the algorithm that we use. And if, let's say, we got a categories that we want to predict, right? Like dogs or cats, or then we use the classification problem. That is, if you go, it's generally classifying based upon the features, we classify the labels, right? So these are the 2 types of supervised algorithm. And then comes the unsupervised algorithms. And some unsupervised algorithms can be used to cluster the data, to create the cluster points that are actually near to each other. So, this is specifically used to explore the data and find one possible way to, help either partially label an unlabeled data set, or, we also get some insights on the nature of the problem that's being talked about in this clustering algorithm, right? And some of the other unsupervised algorithms can be used to reduce dimensionality, which means, right, if you got lots of features, like columns of lots of features of data, and we want to cut down the number of features, or something similar like a principal component PCA, which allows us to, right, throw out less relevant combination of columns, or if there are any redundant columns, we can remove those redundant columns. So this is dimensionality reduction. These are the 2 types of unsupervised learnings. So specifically, as mentioned, classification and in the regression, you'll have features in the data set X, and you have targets or labels in the data set Y. So the goal here is, we fit or we learn the model to predict Y, right? And the classification, something comes as mentioned, dogs, cats, and the regression is like numerical, can be housing prices, and then your numbers, whatever we want to predict, right? So some examples of the supervised machine learning, right? So in this example, if you see supervised learning, it utilizes the data where we know the answer for the outcome. So we already knew what the outcome is. So we also need a model here where we need to actually determine the parameters of the model. right? And if you see the process, this for determining the model, we use the fitting. We fit the model using a pre-built defined data, right, to determine the parameters of the model. Once the parameters have been fit with the parameter, then we predict the model with some other test data, right? This is how the supervised learning works. And in the regression, we'll have movie. Let's say, in this example of the regression, so we got a model that we fitting with the data, movie data with revenue, right? And the parameters are fit with the movie data with revenue, and we pick some data with which we don't know the revenue of, and we actually, after fitting the data, we predict the predicted revenue of the movie. This is an example of regression. And for classification, something similarly, right? We got a discrete label data, right? And we have got a model that we are going to fit the parameters of the model. And then similarly, we use the unlabeled data and predict the model after the model is fitted with the parameters, right? An example we can categorize is, let's say you got emails spamming the spam emails to catch the spam emails. You fit the model with lots of information about the emails which are labeled as spam. You provide the details and fit the parameters, and then you place the unlabeled emails as test data and predict if it's a spam or not spam email. So this is an example of classification. Right, and to calculate the pairwise, right, slowly to come into the context, if you see the classification, for example, right, this is an example where a customer, we have to predict a flower where the customer is most likely to purchase based on something similar to previous purchases. So the features, we can take these as, right, petals, the color of the size and color, right? And the labels, we can predict, what are the actual flowers that the customer is going to buy, right? And so what is needed for the classification, right? So we need to have the features, right? And these features should be quantified. And in the previous example, right? So we can say we may represent a customer's most recent flower purchase with types of flowers, the colors of petals, etc. And we need to know the labels belonging to these examples. And in our flower examples, same. This is the data of which a previous customer actually bought. And the third one is we need to actually know the measure to the similarity between, to measure the similarity between a new record and the ones we learned from, right? And so there are multiple ways to measure this similarity. And let's look at some of the ways we can do that. So to pick an example, right? If you know this this is a very famous algorithm in supervised learning, right? So it's a clustering, this is a very basic, where we can apply the pairwise distance. There are two choices we can make in this KNN, right? So first is the number of neighbors, and second is the distance metric to be used, right? So this is quite a famous algorithm. It's very simple and everyone knows. So for this, right, we don't need any prior knowledge about the structure of the data in the training set. And we also don't need to retrain the data for adding the existing training set. So in this example, where we need to, let's say in this example, where we need to predict cancer survival in patients, right? And the blue dots signify patients that are survived, and the red dots signify the patients that did not survive. And the x-axis, we got the age, and the y-axis, we got, so the x-axis, we got the number of malignant nodes, and the y-axis, we got the age, right? And we can see, we can color, so based upon the supervising machine learning problem, we are actually we can predict the patient survival, right? So now let's say we are using the 3 closest neighbors. K, we are using k is equal to 3 here. And in this, if you see, we are trying to find the nearest neighbors of 3. And we have seen 2 are surviving and one is one patient did not survive. Right, and one more advantage, if this selection of k is it's they go to a lot of iterations. It depends on lots of characteristics. But some examples of picking odd numbers, or it eliminates the ties with the k. It eliminates any ties that happen, right? So here we are picking 3, and in the next slide we see we pick 4, and we are trying to see the closest neighbors. And this is similar. The prediction here, the prediction stays the same. We got 3 blue and 1 red, where the patient is going to. It's more certain that the patient is going to survive, right? So this is how the k nearest, and what is actually needed for the KNN model, right? So we introduced the k-nearest node model before, and what we need is, the first thing we need is correctly determining the k value. And that, as mentioned, right, there's lots of things that we need to consider before selecting the k value. And second, we need to know how to measure the distance of the neighbors, right, between one node to other node, right? And so there are multiple ways to measure this distance. And also the second question also we need to know from this is if some neighbor should be weighted more heavily than the others, right? So we need to identify how to measure the distance. So let's see, we need to see what are the most similar in the model, measures in the model, and what are the closest points that are actually going to be similar in this, right? So the assumption here is that the most common similar points will most likely have similar outcomes. And so how to calculate the distance of these 2 points, right? So if you're using like scikit-learn, this will be automatic. But let's say you're using data evaluations for Python here, right? And you're writing Python code to calculate the distance. And so there are a few choices we can make here. Used to calculate the pairwise distance. The first is a very well-known, which is Euclidean distance, right? Which is hypotenuse whole square is side square plus side square. Everyone knows that to calculate the distance between 2 points is the Euclidean distance is a minus b whole square, x1 minus x2 whole square plus y1 minus y2 whole square, right? So this is the Euclidean distance. And if you see, this is the basic L2 distance, where I got my diagonal as d, and we calculate the square root of node square plus age square, right? This is the L2 basic L2 distance. And other way to calculate is the Manhattan distance, which is L1. We call it as L1 distance. These are the 2 famous and common ways, but there are some problems with L1 distance, right? If there are obstacles and stuff, right? They're calculating the L1 distance, but you just calculating the perimeter or the length of these 2 nodes plus j's, right? This is L1 distance, how we calculate that. So with that, right, as we introduced to the basics of machine learning and the basics of how to calculate the distance, we'll also introduce you to you'll also get introduced to the Intel extension for scikit-learn, right? So the Intel extension for scikit-learn, it actually offers, as I mentioned before, right, optimized versions of many scikit-learn algorithms, and compared to the stock version, they're optimized. And actually, what you need to do is you just need to patch, replacing the stock scikit-learn by just patching it, and there are different ways of patching, applying the patch to the scikit-learn, which we'll see in the following slides. But what you'll do is you will patch the algorithm that you want to implement, and then you run the same code. You fit the model, you train the model, you fit and you predict the model, very similar to what you do, right? And so if you want to unpatch, you can also unpatch. So there are different ways to patch the algorithm, right? So if you got a command line, you can just, if you want to patch an application, you can just say Python my sklearn, and you're patching it here. Or if you want to patch inside a script, or then we'll do from sklearn ex import patch sklearn, and you call the patch sklearn. That's how you're implementing the Intel extension for Python. So for example, in the Knearest Neighbor example, right? In this example, we are using from sklearn ex import patch sklearn, right? And after applying the monkey patch, what we are doing is we are importing the sklearn linear model and importing Knearest Neighbor. And then the other steps remains the same. This is the main point. The top two are the things that you are applying the monkey patch and to take advantage of the Intel extensions for scikit-learn, right? So this is a brief example of Knearest Neighbors, right? And to calculate the pairwise distance here. So once we now come to the calculating the pairwise distance, right? So in this graph, we see there are multiple data points, and the main idea is to calculate the distance between each of the point to other point in this, right? So there are 1, 2, 3, 4, 5 points here, and we are calculating, let's say, distance between 1 and 2, right? So which is P of x1 minus P of x2 whole square plus P of y1 minus P of y2 whole square. This is the distance. This is the distance, and we'll include this distance in the distance matrix. Similarly, we are calculating distance between point 1 and point 3 using the same formula, right? Same thing with D14 and D15, right? Similarly, you now start with the second point and you iterate through all the points in the iteration space, and you calculate the distance matrix, right? So now what we'll do is we put all this into a, finally, we calculate all the distances. This is between all the pair of points, and then we put them into distance matrix. So in this case, right, we got 5 points. It will be a 5 by 5 matrix. And if you see all the diagonals as 0, because this is similar. Distance between 1 and 1 is 0, and 2 and 2 is 0, 3, and so this comes as 0. So this is the distance matrix finally, that is being generated once we calculate all the pairwise distance in a set of points, right? And we already seen the distance formula for calculating the L2 distance, right? Which is something similar to what we've seen. Hypotenuse whole square is side square plus side square. So it will be node square plus a square. So the one thing I want to point here is scikit-learn doesn't support the L2 distance or L1 distance ways of calculating the pairwise distance. And it only supports calculating the cosine distance and correlation distance, right? And this is also similar. Cosine distance is similar to what we've seen, but it's just different mathematics here. These are actually optimized for Intel extensions for scikit-learn. And we got an example in that we're going to demo using the cosine distance, implementing the scikit-learn, calculating the pairwise distance. So cosine distance, if you see, this is the dot product of two vectors, right? There are two vectors A and B. It is the sum of the dot. It is the dot product of two vectors, and we divide it by the length of the vectors, right? So the dot product is simple to calculate. It's ax into bx plus ay into by, right? And the length is, we'll see example here, right? So in this, I got distance of 3 and 4. A vector has 3 and 4 and B has 5, 12. And we're calculating the dot product here. So 1 minus cos theta. So the top product is, the top one is the dot product, the down one is the multiplication of the length. So if you calculate the length of this, it's square root of 3 square plus 4 square, which is 5. And the length of B is square root of 5 square plus 12 square, which is 13, right? So we got the lengths, and we need to calculate 1 minus cos theta, which is the actual cosine distance, right? So we'll see, or the dot product, right? So 1 minus 3 into 5, which is 3 x1 ax and bx, right? and AY into BY. So 3 into 5 plus 4 into 12 divided by the length, which is 5 into 13, right? So now we take a subtraction of that 1 minus the cos theta, right? And we get the final cosine distance. Let's say you are trying to identify the closest nearest points, right? And so we'll pick up this, we calculate this cosine distance and we'll see what is the nearest, what is the lowest value, so that we can determine the nearest distance from two adjacent points that we want to identify. So that is the cosine distance. Correlation distance is exactly similar, but it got a different, a different algorithm to calculate the correlation distance. The sum of the product of the differences between the x and the x mean time, x mean, and it divided by the difference between y. It's a product of xi minus x mean and yi minus y mean, and it divided by the square root of the product of the two sums, right? We'll also see example here. Similarly, A is 512 and B is 34. We got x1 as 5, x2 as 3, right? And the mean of x is mean of 5, 3, which is 4, and mean of y is 12 and 4, which is 8. And we use the formula here, and we calculate the cost correlation matrix. So which is similar to cos theta, cosine, but it's a different, right? And once we calculate the formula here, we'll get the cost correlation distance for this as 1, and actually the correlation distance is 1 minus the correlation algorithm formula, right? So it will be 0 here. So that's the correlation distance. We'll see both examples using cosine distance and correlation distance. So before I go forward, let me look at the chat window, see if there are any questions that I can answer. So,
Yeah, so Praveen, there's one person here, Jameen, that is trying to run the example in the 00 folder. And when he runs the shell script, so run hello.sh, he's getting an error. And I think we've kind of resolved it down to it may be some kind of environment setup configuration thing that he may have wrong. I just confirmed that when I do the git clone and run it, it was running as expected, but he is not seeing that behavior. So,
actually, 00 is just a introduction. If you, so maybe the environmental issue, but I don't know where he's running. Is he running on DevCloud, or is he running on any of the local machine or something?
I'm running on a compute node.
Oh, you're running on a compute node, like a JLSC node?
No, a DevCloud node.
Oh, DevCloud node, okay.
But somehow his Python is set to Python 2, and I don't know how that happened, but he needs to change to Python 3, and that's the underlying issue, and that will, yeah. So I would definitely focus on getting it to the Python 3, and maybe I can kind of poke around and see if I can see something on Stack Overflow or something. I would probably recommend that that's probably where you're going to have to go anyway to figure out what you need to do. I don't know exactly how to get you back to Python 3, but all these labs are going to kind of have the fundamental underlying assumption that it's Python 3.
Oh, yeah, it's good to know. So are you running on JLSC or DevCloud?
DevCloud, we are running on DevCloud, and we are also running on JLSC. But I don't know how your environment got, Python environment got to Python, because DevCloud is a sandbox which actually prevents you from, maybe you had a different Conda channel or something happened, but you can try, I also want to recommend you not to try the 0 module, because that's a very basic, for introduction to Jupyter, but you can come to module 1 or 2 and try a basic example we can show, but yeah, maybe some problem with the environmental.
Yes, I think there's some problem with my environment. Thanks.
Yeah. So is there any other question, Bob, that I can answer?
I think I've been answering them as we go. If there are any others that I missed in trying to address this issue, please refresh my memory. I think I've answered everything so far. So about references and so forth. So.
All right, thanks. Differences.
There were just questions about, you know, is there a good reference for the data parallel Python? And then, so I gave a reference to just that high level, so installation guides and just how to get started and all that stuff. And then I did the same thing for scikit-learn, just so that they know where they can kind of get some more information since we're going to be kind of going through some of this. You know.
Okay, all right. So let me actually switch to the, quickly wrap up the slides and switch to the development amendment so that, you know, we can run some of those, right? So we already, you know, talked about pairwise distance, right? So the main takeaway from this slide is we can actually run it on the dev cloud, but, you know, we are importing the DPCTL library that is required. And here actually, we're not using scikit-learn, but we are using the data parallel essentials for Python here. And here we're using the kernel decorator. And we got X1, X2 are the data points, right? X1 and X2 points are generated, and we are calculating the matrix D. And we get the global ID, which is the, as OpenCL programming style, we get the global ID of that element, and the global ID is individual instance in the complete iteration space, right? So, and what we'll do is we get the shape for X1 and X2 of shape of 1, right? So we get the total number of elements in for shape X2, and we actually iterate in the next loop, right? We loop through the total number of elements in X2, and we calculate the distance matrix, right? So for each element in X2, it computes the pairwise distance corresponding to all the elements. And if there are multiple, this is a multiple dimensions, right? X1 gives the dimensionality of the data set. And if there is multiple dimensions, then it will also calculate, you know, the formula based upon this, right? And so as we've seen, X2 minus X1 whole square plus Y2 minus Y1 whole square. So, and, you know, the distance matrix is computed, and we get the distance matrix here, calculating the square root of it, right? And we can offload to the GPU using this approach, using pairwise distance, right? And using the scikit-learn, the pairwise distance, you'll see we are applying the patch as we discussed from sklearn import patch sklearn. And then we are importing from sklearn in matrix pairwise, import pairwise distances, right? And that's how you use the scikit-learn and apply the Intel monkey patch and get an optimized version for the pairwise distance. And we'll see the pairwise distances. We are calculating the metric as correlation or the metric as cosine. Based upon the metric we passed in, it calculates the pairwise distance based upon the metric we passed in, right? Similarly for Black-Scholes, right? We are using ngit here. And we are using a p-range as we discussed, right? This is an automated, if you're using p-range, it's explicitly or creating a for loop and using p-range. And then Black-Scholes is a very famous algorithm in the financial world where it calculates the puts and calls ratio of a strike price for a particular stock, right? And it will be like every second, and there will be millions of operations that happen to calculate the calls and puts. And, you know, the logic is a little bit out of scope here, but for the Black-Scholes, but at least, you know, the main key takeaway is we got, you know, we use the numba.jit and we pass in the p-range, which is explicitly calling the p-range, and then we are offloading device to compute this in parallel, right? So with that, let's actually switch to the dev cloud, as because, you know, I also actually running on JLS C2. Let me stop sharing the screen and share my dev cloud environment. I hope you're able to see my screen. This is actually the dev cloud environment.
Praveen, can you make that screen larger somehow? It seems like it's just taking up partial real estate. I'm not sure if that's just
the
meeting
browser you mean?
Well, let me see. Maybe it's just on me. Hang on a second. I think I can see it fine. If others are having trouble, let Praveen know. I don't want to mess it up too bad. I think it was me that my screen real estate was too small. I moved through the chats to the side.
So I already showed you how to get access to the course on the Intel Dev Cloud, right? And so I go to Numba-dppy essentials, and the basics we'll be covering here. So we already covered 1 and 2 in the last session. 1 is introduction to data parallel relationships for Python, and 2 is data parallel control. Just a nutshell, right? You can see we can see in the 2 we got how to select a device, right? And I already ran the samples for the interest of time, and actually let me run this sample again now, right? So I just submitted this job to the compute node. I'm actually on the login node, and there is a script called Q that is actually made. It's a handy script. It's a wrapper around the Q sub command. The main command is coming from Q sub ID -L, right? This is the main, and we're passing in the actual workload to the compute node. So this is wrapped around, so the Jupyter notebooks are interactive, right? So you just need to call the Q script here. And once you run that, and you will see the devices that are available on the system, and based upon the different devices that we selected in, right? And similarly, we got the queues, and we already talked about all this. We talked about the USM, developer view of USM. USM is nothing but the unified shared memory, where if you see the USM across CPU, GPU is is broadly grouped, and the developer view of USM, where you can actually share the memory between CPU and GPU using the unified shared memory objects. And there are multiple ways you can create a memory USM device, which can be only on the device. Shared object can be migrated between host and the device, right? And so if you create a USM memory shared object, this is available both on the host and the device, right? And you got multiple functions copying from the device, where you can copy the data from the device memory to the host, or you can copy from host. So we also talked about using the Python uses the buffer protocol to copy this, right? And so this is all what we talked in the last exercise. And just want to I did a brief recap of that. So one of the pairwise algorithms is implemented using the DPCTL memory here. So I'll quickly walk you through this example in this, right? And using the DPCTL memory. So we get the global ID, we talked about this, right? And we get the shape of that. So we are calculating the pairwise distance, and we're adding it to the distance matrix, right? And so we created a xbuff, which we manually copying this. We created a USM shared object with the xbuffs, right? And the ND array, we created an ND array, and using the buffer protocol, this is a USM shared object, right? This xbuff is assigned the shape of x, and we are explicitly copying the x data elements into the NumPy array, right? So this is how we are copying to the creating a USM shared. Similarly, we are doing same for the distance matrix, right? We are copying to the distance matrix to the ND array here using the buffer protocol. So these are USM shared, this can be shared across host and device. And we are calculating the pairwise distance using, and then once the results are computed, right? We are copying the results back finally, right? NumPy.copy to, then these are the result arrays, right? And these are result array. and we're copying back to the distance matrix. We already covered this, so I just want to cover, as we are talking about pairwise distance here, using the one of the approaches we used in the memory USM memory shared approach. And we talked about the compute follows data, right? And this also compute follows data approach, where if you see, we can actually use this in the pairwise distance. So I'm going to the third module 3. I got pairwise distance here, right? And so we already talked about this. All these are clearly detailed, right? The distance matrix and calculating the L2 distance. There is an example for you to calculate L2 distance. And so this is the main things that, the command line parameters that we are passing in to each of these examples. If you pass the steps, right, as 10, so this will be the number of workload runs, the number of steps you provide. So if you see one of my example here, right, I'm passing in steps as 5. The initial size is 1024, right? And if I come here, the steps, if I don't pass anything, it will be 10. Initial size of the data array, if you don't specify anything, for pairwise, it is 2 power 14, but I can specify to make it small, right? I specified the size as 1024, right? And repeat is, the more workload you want to apply to a GPU, right? So if repeat is 1, it just iterations are just 1. If it's 5, right, it calculates 5 different times the pairwise distance. And the other consideration is data dimension, right? If you want to create a 3-dimensional array, 3-dimensional point or 2-dimensional point, right? You can actually manipulate this in providing the command and parameters. Another important thing is using USM, -USM. If you are using USM, then you follow the compute follows data approach, right? And what is compute follows data approach? And if you see this example here, I'm not passing compute follows data approach, but if I see the kernel approach, I'm using I should be using -USM somewhere here. I'm not using anywhere, but I can actually provide a, for kernel approach, I can provide a -USM. And what it enables is, and I can run this command, right? What is the commit change to? Let me, okay, this is kernel, Pairwise kernel.py. And the kernel approach is, we already seen that. We're getting the global ID, right? So this is what we talked about, X1, X2. We're getting the global ID. And we're iterating through the points to calculate the distance matrix, right? We talked about the logic. If I include the USM, it actually uses the USM approach. And with the, let me actually show you what happens in the USM mode, right? If I go to lab and it calls this kernel mode calls Pairwise graph.py. And so this is nothing but, it generates this sample, this Python file generates the data randomly for Pairwise Python for the points, right? Based upon the command line parameters you provided. It selects the GPU or CPU, whatever the device selector that you passed in. And it generates the data as I mentioned, right? If I'm using the USM, it follows the compute follows data. So it's generate data USM, right? And I got Dpctl.device context, select the device. Actually, I don't need to, because compute follows data is specifically saying that the data, the compute happens wherever I pass in the data, right? So this is not required specifically, theoretically. So, and then I created a DPT tensor, Dpctl.tensor that we talked about, right? This is a Python array specific API, Python array API. We are calling USM underscore ND array, dptensor.usm ND array, right? And the main thing is the buffer type is device. The device we're passing in as the GPU here. And we're passing in the Q as GPU Q, which is the Q, which is GPU Q, which we define. So this is a compute follows data approach where we are creating the data. We are actually copying the data to the device using the USM ND, USM DP controller tensor, right? And then we are actually passing in the device with the data so that, the data is, the compute happens where the data is residing. Similarly, we did for X USM and Y USM, right? These are X and Y points. And we are doing the same for the distance matrix here. Exactly the same thing, right? And then as these are happening on the device, so now the computation is happening on the device. We come back and once the computation is done, we are actually, first we are actually copying from host to the device, right? So now we are copying, we are manually explicitly copying using copy from host. And then, once the computation happens, we return the X USM by USM because these are USM shared objects. We're creating X USM by USM, passing in the objects, returning the objects. So this will be accessed on the host side. And so yeah, this is the actual compute follows data approach. And let's see what happens on the right. Yeah, so I passed in size steps of 5, 1, 2, 3, 4, 5. Initially, I started with 1024, right? And the size incremented by 2, which is steps again here. And that's how you can actually manipulate your data and run your examples to actually, check the workload and right. So this is the kernel approach, and we ran a GPU result. Actually, let me show you the example where I actually already have a pre-built.
Hey, Praveen, I know you're on a track here. I was just waiting for a point to interject. Jiming has a question about, do you recommend using the USM or buffer for Python programming with offloading support? So when you get a chance to swing back around to that.
Yeah, so this is the compute follows data approach is going to be the, so eventually this will be the main approach that will be followed because this is Python based on Python array API specific. So the compute follows data is, I think, preferable, but there is no call out on the performance exactly per se on that, but the strategy towards the compute follows data approach. So the suggestion is to follow the USM approach, but there are some easier ways, but the USM approach is only used for kernel. If you're using ngit, right? If you're using ngit here, the USM approach doesn't work because the USM only works on the GPU style programming. So this is ngit, right? And this only works without USM. If you pass USM, it will fail. And
when it's engine, do you mean the driver code? What does engine mean? What does engine mean here?
Oh, ngit. If you see,
what does it mean here?
Okay, let me show you that, right? Numba.jit, right? Ngit.
Oh, sorry. Oh, sorry. I confused it with engine. Engine.
Oh, yeah. So this ngit is, your explicit, as I mentioned, explicit and automated offload using the P range or using the NumPy arrays, right? I'm trying to see how I can hide this.
So what you are saying is that with the NJIT declaration, USM USM doesn't work along
exactly
with NJIT, right?
Exactly. Yeah, it only works with the kernel approach. The USM works.
Oh, okay.
I'm trying to find this magic wand. How can I hide this? It's not going away. So, all right, I think it's here. So I'm on Pairwise. Okay, so I already generated. So yeah, so this is in the interest of time, right? So we just experimented plotting the GPU results here, right? And so the same Pairwise we ran using the, here we didn't use the USM approach, but we used, we used the kernel, but we didn't use USM, but we plotting the graph. Actually, what we see is the closest, we are trying to plot the Xeon pairs of points that are closer. So cyan, we're trying to match them, and I colored them as cyan, which are closer to pink, right? The same thing as I just picked the first 10 elements, ran this, generated the data and ran it. And I just, use the first 15 elements probably, and, tried to plot in the graph shows, the cyan is, the closer where, the blue, we're pointing the cyan points which are closer to the blue, right? That's what we're trying to, just a experiment, right? And there is also, we can use a NumPy approach, which is, clearly detailed here. So let's actually run through create a roofline, and analyze the roofline report, right? So we talked about advisor roofline analysis, right? And I provided the commands. Generating the advisor commands takes a lot of time, so we can't actually run them live, but so let's talk about the roofline, right? In order to generate a roofline analysis report, so your application must be at least partially running on a GPU or Gen 9 or Gen 11. And right, it might be implemented using SYCL code or parallel Python code or something, right? And so generating a roofline generates a multi-level roofline where actually every single loop generates several dots, and each dot can be compared to its own memories, something like GTI memory, the L3, right? So let's actually, I ran the report and actually show my report here. Are you able to see my screen? This is also, I charted a browser. Bob, are you able to see my screen?
Yeah, I can see your screen, Praveen.
With the Pairwise, with the roofline chart?
Yes, I can see it.
So
there's a note here too, just maybe to go slower. So if you can slow down a little bit, and then there's a question. Everybody can see the graph. There's just a question about Barbara, I believe it is. I went to devcloud.com, get started, and she got a menu for the C++ module. She wanted to know how to switch to Python. I'll see if I can go to that site and figure that out myself. But I did want to just call out that folks are struggling to keep up with you. But
oh, sorry, thanks. Yeah. So yeah, let me be a little bit slow here. So I mean, I saw the question, so he was confused with sorry for being a little bit fast, but confused with the kernel approach. So is the question saying the confusion with the kernel approach? It would be great to compare USM, NJIT, and other approach you write. Okay.
Yes, maybe you could use a simple example to show different approaches like USM, NJIT, and other
sure.
approaches. Yeah, I think I know you have done a lot of work. That's very great.
Oh yeah, no problem. Sorry for being fast. Yeah. So this is an example using NJIT, right? NJIT, and we are using. This is explicitly we're creating a P range, right?
Yes, yes.
And I got my points, x1 and x2, right? And what you're doing is for I in numba.p range, right? That's how you're explicitly calling the P range to offload this to a parallel loop over the matrix x1. And for matrix x2, the same thing, this internally, right? It runs in parallel. We are iterating to the map for each element in matrix 1. We iterate through all the elements in matrix 2, right? And then if based upon the number of dimensions, we calculate the dimensionality and we calculate the distance matrix, right? And if I come to a kernel approach, the same thing, right? X1, X2, instead of doing a P range here, I got numba.kernel. This is GPU programming style. Now I get the global ID, the total number of elements in this particular, right? So this of the matrix, I get the global ID of I, which now I get the X shape. So for this is single individual index of, so that's total individual elements in the complete work items, right? So now I iterate through the X2 and then do the same computation. So I'm not passing any p range here. I'm calling the OpenCL style to get the individual item instead of doing the iteration through this in matrix X1 previously, right? That is using kernel approach. And NumPy approach, if you see the NumPy, we are still using ngJIT, but here my data items are all NumPy. This is automated, right? I'm not calling any p range here.
Right.
And these are all NumPy. The data is all NumPy. And we're doing the same computation without passing any loops here. So this is automatic offload using the NumPy approach, where this is actually, calculating in parallel on the device side. I hope you're clear on that, right?
Oh, yes. Oh, thanks. I think it's good to explore your work. You have done a lot of work.
Oh yeah, thanks. Yeah, but I was trying to clear the cover the roofline, but I'm sorry. I think I was a little bit fast on that. Okay. And where is my window? I opened. So to make it on the roofline, right? So each dot, as I mentioned, each dot represents a loop that actually, compared to its memory. And if you see this, if you see the chart, it is not only, we'll see where the bottlenecks exist, but actually what's actually likely causing them and which ones will provide most speed up if it's optimized. The axis on the x-axis is arithmetic intensity, and the y-axis is gigaflops. Arithmetic intensity is, it's nothing but a calculation of flops with, it's a ratio operation or ratio of performed, operations to the bytes axis. So that's a calculation of the arithmetic intensity, right? And so it happens two things, right? First is it calculates a survey which runs the system benchmarks and the timing of the data with minimal overhead. And the second is trip counts and flops, which calculates through the trip counts, right? And so two things. One is survey, right, which calculates the timing. Second is trip counts. And this trip counts is calculating the overhead of collecting memory traffic and the flop data, right? So it calculates all the roofline, it calculates all the data. And we can see the diagonal lines, right, which talks of different memory limitations here. So the dots on the roofline chart are correspondent to the particular OpenCL kernels or the loops, right? And we got three different types of these graphs here, right? The SLM, shared local memory, the GTI bandwidth, which is the GPU memory read bandwidth, and which access between the GPU and the main memory. And the third is shared local memory, L3 bandwidth, and GTI bandwidth. The DRAM is dynamic random memory access. And if you see this, this is memory bound, and if it's come to the extreme right, this will be compute bound. But this shows like a GPU is memory bound, and you can still see this is 11 gigaflops, and it can show the improvement. It can be made till 19. If you see, click on this, right, you will see the number of flops that it can still reach. The roof it can still attain. So overall, right, we are seeking to understand what is maximum achievable performance with your current hardware resources and your application, how it's performing with your current, memory bandwidth and the current hardware resources, right? And if you see the dot towards extreme right-hand side, then you'll see, these are all the double precision add, double precision, multiplier, single precision, add, and single precision multiplier. So if the dots come to the horizontal lines, then that is compute bound applications, and that's how you can actually generate this. And you can actually click SLM L3, and you can see the different dots, right, for this. So this is a roofline analysis. Just a time check. Ray, how much? What is the? How much time still we have?
Well, officially we have until the top of the hour, but if you need to go over a few minutes, I think that's okay.
Okay, thanks. And let's go back to the Pairwise and all right. I'll also show you the same mechanism using vtune, right? I actually wanted to run the vtune, but so we ran the advisor commands and generating the vtune reports. So vtune, we generate two of the reports here. One is the GPU offload analysis, which enables the GPU optimization option to explore GPU. It identifies the GPU usage, the GPU idle times, the most active computing tasks and stuff. And there's other hotspot, GPU hotspot that we generate, which actually, it identifies what are the actual hotspots and in your application, what are the floating point metrics that you used. And so you can generate this, right? I can pass it based upon the metrics I gave you before. I can generate vtune, collect GPU offload, right? And I'm passing with kernel, steps of 1, size is 16,384 and dimensionality as 3, right? So I created some vtune analysis charts here, which you can refer through. So this is just for CPU. And let's look at the GPU charts, right? So this is for one-dimensional GPU USM, right? This is one-dimensional GPU offload. You can see the elapsed time, right? The total GPU time is percentage of elapsed time. The total elapsed 12% is spent on the GPU, right? And you can see the top hotspots when the GPU was idle, and you can see the hottest tasks here, right? You can see multiple information, but just for a experimentation purpose, right? So let's look at the USM hotspots, right? It gives the elapsed time and the GPU time, and it also gives you information about array stalled idle time, which is 48% of elapsed time with GPU. So it says that the GPU is waiting 48% of the time, which is bad, which is not good, right? So it is stalled and waiting, especially for compute bound applications or something, right? The GPU is waiting on something, and we have to see what we can increase. And if you see the GPU L3 bandwidth bound, right, it shows how much cache it's using. So it's 30% of peak value, which is not bad, but it's still, we can make it better, right? So this is with one-dimensional. I just tried the same with three-dimensional, right? And for one-dimensional, I did, if I create a three-dimensional point, I see a little bit GPU time is more time spent on the GPU, right? And you look at the GPU hotspot for three-dimensional and GPU hotspot difference, right? So I'm able to reduce the stall time to 40% from 48%, right? And my GPU L3 bandwidth is now it's increased 37%, right? It's using more cache, which is, I'm doing bad in that. So these are the different types of experiments you can do. And if I run, it will show you the command that it runs. If you see, it shows you the FPU utilization, the floating point units. And this also, we need to make sure this will not be the highest. It will not overtake. If it's 90% to 70, 80%, we need to see what's causing the usage of more floating point operations. You can collect a lot of information. And I tried randomly, right? Some X number of points, and and now I'm spending a lot of time on GPU, right? And the stall time is reduced, but my L3 bandwidth is so high now, I'm really bad here, right? The GPU L3 bandwidth is now, it's using a lot of cache. It's waiting. It's actually, it's using 90% is L3 bandwidth bound. And you have to see the options like, localization, temporal localization or spatial localization, and see how we can actually optimize our application to reduce the usage of the GPU L3 bandwidth. So these are the different kinds of analysis that you can do using the vTune. You can actually run these reports, right? I gave you the commands here. Get an interactive node. You can run on the compute or the login node. You can get an interactive node and increase the dimensionality. The size, make sure you're not high on this, it's actually 16,384 is the max for Pairwise that is this application is accepting. If it goes beyond that, there is a memory issues. So the max this is taking is 2 power 15, which is 16,384. So you can play around with multiple options over here, creating the vTune chart, right? And so there's a vTune, and let me quickly cover the scikit-learn for Pairwise for scikit-learn. So this example, right? This is in the, if you go on Pairwise and click on the module Pairwise cosine correlation, click on this, right? So the main objective here is where, I gave the complete instructions of how to enable the scikit-learn patching and stuff. So you import from scikit-learn, call the patch scikit-learn example, right? And so this simple example started with dbscan using scikit-learn, which we don't need to do that right now. And, so all the scripts are given here, but let's look at the actual exercise here. Right? So the main idea behind this application is, we had this example is, we are trying to identify 5 closest to near stocks that are actually, behaving in a certain pattern or a certain amount of time, right? So we collected a set of points, 500 amount of stocks, and we read this data, right? And plot the whole portfolio at once to get, so, we are plotting these graphs, all the portfolio of, to fill the data, right? It's a whole set of 500 set of stocks that are behaving respect to time. And we just, plotting, like for example, 4 or 5, how these actually look in the real time, right? What is the tendency of the stock or the time value series based upon the time. And we want to, based upon the previous 500 generated stocks, right? What we are doing is, we are actually trying to identify 4 patterns, which we want to compare our using scikit-learn. And I run this, and I see these are 4 different patterns. One is going down, one is like cyclical, right? One is going up and down. So let's say you want to compare against blue and orange, right? Which one is going down and one is in cyclical shape. And here we use the pairwise distance using the cosine matrix, right? And so similarly, we apply the patch here using scikit-learn, pair patch sklearn distance, right? And you're importing the pairwise distance, and we're passing in the pairwise distance here, and passing in the matrix as cosine. And to fit in the pairwise distance, we actually reshape the shapes in that, and to accommodate the pairwise distance function. And the matrix we passed is cosine, right? And what we are trying to show is, find the stocks, at least 4 nearest stocks that are following the blue line trend, which is going down, right? So I run that, and it enables the scikit-learn approach, and in the pairwise distance, it identified 4 time value series or stocks that are closest to this distance, which is, this is using cosine distance matrix. And similarly, using correlation, this is the correlation matrix we used. And if you run this, it finds the next 4 closest, which are actually cyclical in nature, right? Which goes ups and down. And based upon this nature, we identified the stocks, that are using the correlation matrix and the closest stocks using pairwise distance that are following this trend. This is an example for you to give how to take advantage of pairwise distance using scikit-learn and identify something that are closest in a real world scenarios, right? So that's what is the coverage on pairwise distance. I want to cover Black-Scholes too, but I think I will do it in the next series. But something this is very similar, Black-Scholes, because we are over time here. But Black-Scholes is doing the same. I generated the exact same graphs, and we can actually go through these graphs in this module in the third part 3, which we'll be covering more of these type of examples. Part 3 will be planning to cover some k-means. G-pairs is one good example where we'll try to show some examples of usage of the GPU programming using local memory access and stuff. But that's what is planning for the third part, which is on June 8th. With that, I'll take any questions, but I can wrap up the session with my slides. We cover lots of details about the pairwise algorithm using scikit-learn and using the numba.jit decorators, the kernel decorators, right? We talked on the vtune reports and the advisor reports. Thanks a lot for attending the session, and with that, I'm open to take any questions. Sorry for being a little bit fast, but I tried to cover Black-Scholes, but we can do it in the next time.